Hi everyone, in this video we'll introduce PoseAugment, a novel generative human pose data augmentation method with physical plausibility for IMU-based motion capture. Human motions provide rich interactive information for many applications, like animations, movie production, and healthcare. Capturing human motions from sparse IMUs has many advantages compared with CV-based methods, like it is not affected by occlusions and has better power efficiency, thus becoming an important research topic in recent years. Here we will show some examples. The IP first captures full-body poses from 6 IMUs in real time. The IMUs are mounted on 2 wrists, 2 knees, head, and pelvis. Beyond that, Transpose also captures the global translations using the same IMU configurations. And IMU Poser further reduces the IMU numbers to daily settings, only using 1 to 3 IMUs from commercial devices. However, these methods all require large IMU and pose dataset to train the mocap models. High-quality pose data can only be collected by professional mocap systems like OptiTrack, which is both expensive and time-consuming. To this end, we need a high-quality data augmentation method that follows the original data distribution in both the pose and IMU data spaces, while providing enough diversity at the same time. Previous human pose generation methods often fail to do so because the generation process are mostly conditioned on high-level actions or text descriptions. Therefore, the data space can be varied significantly. Instead, we found that pose augmentation in a motion-to-motion manner can preserve the IMU motion space to the maximum, thus achieving the best performance in mocap model training. We propose PoseAugment. It incorporates 2 stages, including pose data generation and physical optimization. After the pose data are augmented, we synthesize the corresponding IMU data to train motion capture models. In the first stage, we learn a VAE model to generate new poses based on a given pose sequence. The encoder encodes the difference between 2 frames to a distribution in the latent space. Then a latent vector is sampled from this distribution, and the decoder will use this latent vector to reconstruct the current frame from the previous one. This frame can then be used in the next iteration to generate new poses frame by frame autoregressively. Then the second stage leverages physical constraints to optimize the motion artifacts. First, the desired accelerations are computed from the generated poses using a dual PD controller proposed by PIP. Then we use physical constraint on these accelerations, reaction forces, and internal torques to optimize the motion dynamic properties. Finally, the final augmented poses can be simulated from these dynamic properties for synthesizing the IMU signals. Here are some examples of generated poses. The green pose is the original ground truth, while the red ones are 10 pose sequences generated from the original sequence. We can see that the red poses form a motion space around the original pose. This could help the mocap model to learn the motion distribution, but not only a single motion, thus improving the model generalizability. Here we visualize the IMU accelerations synthesized from the original pose generated from the VAE module, and poses optimized by the physical module. The generated and optimized IMU signals all cover the IMU space comprehensively, but the optimized IMU signals are closer to the original data, and the signal jitter is significantly smaller than the generated data. We compare PoseAugment with adding random noises and 4 typical previous pose generation methods in training mocap models. PoseAugment achieved the lowest motion capture errors in most situations, revealing a strong potential of our method in reducing the motion data collection burden as well as improving the model performance. For more details, please refer to our paper and code. Thanks for watching.